Okay, recording here. October 12, 2021, Physics 37. Okay, let's summarize what we have done so far. So you can situate yourself. Many of the ideas that we have discussed, they build up towards another one, okay? So many of the ideas that we discussed before, we are reusing them here. That's what I mean, okay? 10, 12, oh, let's go. 10, 12, 21, okay? So many of the ideas that we used before are being used again in a different way. Right? So, so what do we start doing? We started with one-dimensional motion. That's what we started. You know, position, displacement, what else? Velocity, right? And acceleration. That's what we did in 1D, right? Found equation. What else we did? Found equations of motion for constant, for two different cases, for two different and important too, not just important cases. Constant velocity, that's one. And I'll even put in the other line here. Here you go. A, constant velocity, and constant acceleration. Just because it's one dimension doesn't mean that we are not going to use in the two-dimension case. We are going to use it. So what's happening here? We are creating new ideas, and we are using the old ideas in conjunction with the new ideas. That's what we are doing. Okay, so we started with one-dimensional motion. Followed with 2D motion. But because it's a 2D motion, now we have to use vectors. Okay, we have to use vectors. And the 2D motion, we still have position, okay? Vector, but now we have what? We have vector position. We have vector displacement. We have vector velocity and vector acceleration. Did you get the idea here? Right? So we did the case of, there's a bunch of cases that we can use for two-dimensional motion, but the one that I concentrated on was what? Was projectile motion. So important that we did a lab on that. Okay? And the other one, what was the other example that we did? What was the other example that we did in two-dimensional motion? Remember check your notes, or try to consult your brain there, your memories there in your brain. What was the other projectile? One example of 2D motion was projectile motion, and the other example was what? Was that? Yep, circular motion. Did you notice that we're going back to circular motion right now? Right? Okay, so that's what we did for motion. Okay. Okay, in projectile motion, projectile motion is nothing but a combination of constant velocity in one. Okay, here you go. Refer to that here. Constant velocity in the x direction, with constant acceleration in the y direction. Right? See that? We are using the same ideas that you are introducing one-dimensional motion. Here is a little bit more complicated, a little bit more difficult. You know, it's not constant velocity, it's not constant acceleration. It's constant speed. Okay, here you go. We have even going to classify here uniform circular motion. No, it's not constant velocity, it's something else. It's constant speed. Okay, which is different from velocity. Constant speed, but variable vector velocity. The vector velocity changes because it's changing direction. The length of the vector velocity is not changing, but the direction of the vector velocity is changing as the particle undergo uniform circular motion. Okay? Constant speed, but variable vector velocity. What else? Ooh. Go. What else? Constant magnitude of the acceleration vector. Magnitude of the acceleration vector. Okay. But variable direction. See the difference? It's just like the same case as the velocity. Constant speed, but variable direction. Ooh. Variable direction of the vector velocity. Constant speed, constant magnitude of the acceleration vector, but variable direction. That's what we did for motion. And then what we're doing next. Here we go. Then we start looking at Newton's law of motion. Newton's laws of motion. Okay? Previously, we just studied motion. Doesn't matter how the motion arises. But now what we are doing, we are studying how the motion, how type of motion arises. A motion arises because of Newton's law of motion. That's why it's called laws of motion. The reason for a type of movement has to do with the force. Okay. Paragraph. Here you go. Newton's law of motion, which employs the idea of force, the concept of force. Okay, it is a set of forces that is responsible for the type of motion. Okay. So what did you learn? We learned that net force, 0. Object either at rest or moving with constant velocity. Net force different of 0, we have an acceleration. See how things are accumulating? We are reusing those ideas that we saw before. So if you didn't understand the idea of acceleration, you are going to struggle to understand Newton's law of motion. Okay? Net force difference of zero, we have an acceleration. And we came up with the idea of interaction too, right? Interaction between objects, force between objects. Just another way of explaining that. So we did examples for the linear case, and now we are looking at examples for linear case, I mean one-dimensional case, for one-dimensional case. Now we're going to look at examples for two-dimensional case, specifically circular motion, in the case of circular motion. So whatever you learned about circular motion before, we are going to apply again here. Okay, and let's not forget, not only I talked about uniform circular motion, I also talked about non-uniform circular motion. Non-uniform circular motion, which is more difficult than the uniform circular motion. This is a summary what we have done so far. Okay. One-dimensional case. What we did here, for example, one-dimensional motion. Object under acceleration. We also looked into apparent weight, right? That's my favorite subject, apparent weight. And now we're going to do examples of two-dimensional motion. And here you go. That's what you have to know, right? That's what I told you before when we were looking at uniform circular motion. Let's see if that's the one I want. Let me, bear with me a few minutes. I don't think it. P37. Oh, where's my P37? Huh. P37, okay, here. No? Okay, I'll stick to that. Here you go. If I want to, play a movie for you, right? I like to do that in my classes. Play a movie, right? So, how do? I start with the x-axis, right? Start with the x-axis, move to the y-axis. That's what we do in physics, okay? Set up the axis first. Then the type of motion, right? The type of motion that we have, circular motion. We put the particle here in the, let's see, let me erase everything here. Oh, okay. This one, good. Okay, here you go. I put the particle in there, right? That's how I call playing a movie. Get used to that. Try to play, get this habit of playing a movie inside your head, so you can solve the problems more easily. As you play the movie in your head, you also put that in the paper. Right, write that down in the paper. Here you go, x-axis, y-axis. The path of the particle is going to be circular, and then we put the particle somewhere along the in the circle, and we identify the vectors. Oh, by the way, I gotta put. I gotta. Oh, what is going on here? I say that the particle has a velocity. Has a velocity? No, has a mass. Okay, here you go. Then I illustrate the velocity vector of the particle. I need to put down too that the radius of the circle here. Let me put the radius of the circle here. Here you go. I'm gonna use radius radius here, radius there. Ooh. Oh no, I put it upside down. Here you go. Minus radius here, minus radius there. Minus radius there, right? Here you go. Particle. I gotta copy and paste this one too. Here you go. Radius, radius, radius with the velocity vector. I don't need this not. What else? Then we have the acceleration of the particle. Let's not forget about the radius too. I use lowercase r. Yeah, I use lowercase r instead of. But that's okay. And you have to know. You have this unit vector, radial vector, away from the circle. What else do you have to know? You have to know that one here. You have to know that there is a net force as well, which, by the way, is coincides with the direction of the acceleration vector. Okay, here you go. Acceleration vector here, net force should be. If that's the only acceleration that we have, it means that the net force will have the same acceleration of the same direction of the acceleration vector. Okay. So, and this net force, because we have just a central force that points towards the center of the circle, this net force coincides with the centripetal force, which is proportional to the centripetal acceleration. Okay? Let's play the movie again. Here you go. That's how you do when you are solving those problems, right? You draw x-axis, you draw y-axis, you draw a circle. For this type of problem, you have to draw a circle. You gotta put the coordinate, the radius of the circle, situate the particle in this circle. Gotta say that it has a mass, it has a velocity vector, has an acceleration vector. In this case, is uniform circular motion. Consequently, we have only centripetal acceleration, no tangential acceleration. I am illustrating here the fact that we have a unit vector in the radial direction that's contrary to the centripetal acceleration. And because we have only one acceleration, which is the centripetal acceleration, the net force coincides, the direction of the net force coincides the direction of the centripetal acceleration towards the center, centripetal towards the center. That's why I'm putting here F net equal to centripetal force. What I started doing last time, I started to do the problem of the conical pendulum, right? I've introduced to you what are the technological applications of the conical pendulum. Okay, one of the technological applications of the conical pendulum is in timekeeping devices. Another technological application is that the invention of the James Watson, right? James Watson or Thomas Watson? The guy that helped with the Industrial Revolution. So he used a conical pendulum in one of his engines, which was a device. It is a device called the governor that's used in a internal combustion engine, right? So there are applications for this device here. It's not out there. It's not. No, I just want you to solve this problem. No. There are applications for something like that. Okay. And we didn't finish, right? We didn't finish solving this problem, right? We have this object describing a uniform circular motion in this plane. I call that XZ plane. And I need you to identify the first step that you have to do. You have to identify the forces acting the object. It is attached to a string. The string is length L. You have a mass. All right. Let's take a look at the enunciate of the problem. Right in here, circular motion. Okay, here you go, right in here. Conical pendulum, a particle of mass m suspended by a string of length L. Particle moves at a constant speed in a horizontal circle. Constant speed, but not constant velocity. The radius of the circle is r. Find the tension applied to the string and v in terms of the other parameters. So let's find the tension first. Notes. How far did I go? I didn't go any far, right? I just introduced the problem of the conical pendulum. I didn't write any formulas, right? So solution of the, let's see, first uniform circular motion. Okay, doing the conical pendulum. Yeah, we didn't do anything. Conical pendulum. Example, conical pendulum. Okay. What you know the mass, you know the radius. I'm gonna put a capital R. You know the speed, but not the velocity. You know the string is L. That's what you know. So when you solve your problems, make sure you write down what you know and what you don't know. That helps you solve the problem. Don't rely on your memory alone. Mass string. Okay, find the tension. Okay, find the tension. Here. You know that this guy here is constant. You just don't know the value. Okay, you know that it's constant, but don't know the value. L. Find tension. Apply to M and V in terms of the other parameters. You know that V is constant, but you do not know its value. Constant unknown, constant value, constant value, but let's see how constant but unknown value. Let's put it this way. Solution. You have to understand what the problem is asking first, right? Before you start solving it. If you don't understand what the problem is asking, and in order for you to ensure that you understand what the problem is asking, you summarize it like that. Solution. Let me get some of my vectors there. Okay, I have a vector here. Here you go. Solution. That's what you're gonna start. Net force is equal to mass times centripetal acceleration. Example, conical pendulum. Uniform circular motion. Uniform circular motion on the x dash z plane. Okay, so that's your starting point. Okay, and what else you have to know? You gotta identify the forces. You know that you have a weight and you have a tension. Okay, and that's what I want to find out. You want to find out the tension. Oh, what else? I didn't write it down. Let's see here. Did I write down that we know the... Oh, I didn't write that down. Yeah, I wrote down that we know the radius. Good. Writing here. Okay? So the net force becomes what? The net force becomes tension plus mg. I'm gonna put it tension here, weight here. This is a vectorial equation. And because it's a vectorial equation, you have two scalar equations there. Okay. Remember, this particle is suspended in the air, right? By the string. It's not touching any surface whatsoever. So there is no normal here. Okay? There's no normal here, no contact between surfaces. So let's break it down, this equation, in the x and y components. Okay. So I'm gonna write down Tx. Since I'm gonna write down the scalar equations, I don't need the vectors there anymore. Tx plus Wx is equal to Max. Let's see, I'm gonna write down, yeah, what's going on here? Yep, centripetal acceleration in the x direction, let's put it this way. And I don't need that. I am assuming that if there is any sign in there, the sign is implicit. Oh, I'm gonna put Wx here. Wx. And then I can repeat that for the y. We worry about whether they are 0 or not later on. I'm assuming that if there is a negative sign, the negative sign is already implicit there in the expression. Okay, so here you go. Do we have x component for the tension? Yes or no? Do we have x component for the tension? Maybe I illustrate that here, did I? No, I didn't. Yeah, I did illustrate it. Yeah, we have an X component for the tension. Okay? And the X component for the tension is going to be T cosine of this angle here. Okay, so here you go. We write down T cosine. I'm gonna call that angle theta. Cosine. Do we have a X component for the weight? Yes or no? Do you see here an X component for this weight here? Huh? All the weight is along the y-axis, right? So I'm gonna put it 0. And then do we have that the centripetal acceleration has a X component? Yep, the centripetal acceleration has an X component, whether, you know, I'll even call it, instead of X component, I'm gonna call it horizontal component. It's better. Here is an X component. Here is an X component. Here is a combination of X and Z components. Okay? But let's call it horizontal component. We can solve the problem right here, this spot. You can solve the problem right here, this spot. You're not going to lose any information if you do that. So yeah, we do have a X component for the centripetal acceleration. And we will worry about this equation later on. Do we have a Y component for the tension? Yes or no? Take a look. Yeah, we do have a Y component for the tension. Right in here. So let's write that down. Do we have a Y component for the weight? Yes. Is it positive or negative? Is the weight positive or negative? Okay, so we write that down as negative. But then I'm going to write that down as the whole thing, minus mg. Do we have a Y component for the centripetal acceleration? No, right? So it's just, the acceleration is just along the horizontal direction. So I'm going to put that 0. Motion along the horizontal direction is an accelerated motion. Motion along the vertical direction is accelerated motion equal to 0. Here we apply Newton's first law, here we apply Newton's second law. Okay? So let's see if we can, we still do not know what theta is, okay? But let's see if we can substitute for other things. We can substitute for this for centripetal acceleration, right? What's going to be the equation for the centripetal acceleration? Gotta know that by heart. What's the equation for the centripetal acceleration? Refer to your equations, right? Go. V squared over what? Over? R. Yeah. V squared over R. Does it have units of acceleration? Does this formula has units of acceleration? Yes or no? You have meters square. Oops, not T. R. You have meters square per second square upstairs. You have meters downstairs. Meters downstairs cancel out with one of the meters square at the top. We get a meters per second square on the right side. Makes sense, right? Dimensionally makes sense. That's one way of testing if your equations are correct or not in terms of dimension. I can get rid of this 0. And now I'm going to concentrate on this theta. This theta so far is unknown, right? So far we have the following unknowns. So far we have the following unknowns. You know, theta, t, and v. Those are the unknowns that we have. 3 unknowns and 2 equations. Can you solve this problem? 3 unknowns, 2 equations. Can you solve this problem? This basic algebra, right? In general, you need the same number of equations for the number of unknowns. In general, you need 3 equations for 3 unknowns, in general. Okay? Unless one of the variables is dependent on one, unless one of the unknowns is dependent of the other, okay? But we can get this third equation. It's possible to get this third equation. How do we get this third equation? Going back to the drawing. See, we have L and R, right? We want to find this angle here. L divided by R is equal to what? No, sorry, R divided by L, right? R divided by L is equal to what? Huh? Okay. We can get a third equation from the drawings, from the drawing. Okay, so the third equation, I'm gonna copy and paste that below and write down the third equation. The third equation is R divided by L is equal to cosine of theta, right? You go. Like that. Now we have 3 equations for 3 unknowns. I'm going to highlight the unknowns. This is an unknown. This is an unknown. All we know about V is that it is constant. And this is an unknown. Oh. T is also an unknown. Go. I'm going to highlight now. I'm going to boldface the unknowns. So the first unknown was solved. We know what the first unknown is. Okay, so here we go. The first unknown, the theta, right? The unknown theta. We know. Let's substitute it there in the problem. I'm gonna use here the cosine of theta is going to become R over L. So we use this one. This sine of theta is going to become what? We can change the sine of theta. We can do the, the trigonometric substitution, right? The square root. Cosine square plus sine square equal to 1. Okay, becomes 1 minus cosine square. Minus cosine square. Well, we are not done yet. Okay, cosine square goes right in here. you go. We don't need the theta anymore, right? Because the theta went away. Huh, what a shame. Huh, try it again. Good, good. Okay. That's what we get. Now we can get rid of this equation here. We don't need that anymore. What was 3 equations now became 2, because we used one of them. Now look here. How are we going to solve this equation now? I'm keeping track what we know and what we don't know, right? What would be the most efficient way to solve this problem? Tell me what would be the most efficient way of solving this problem. We want to know, now we want to know what's the value of v in terms of the other parameter and what's the value of t in terms of the other parameter, or in terms of the known parameter. What would be the most efficient way of solving this problem? That's when you have to stop, and think, instead of keep on working like crazy and spinning our wheels. Happens that all the time. You're so anxious to finish a problem, you start to, shoot in every possible direction, wasting energy and wasting ammunition. What would be the most efficient way of solving this problem? At least part of the problem, right? We have to find out, we found out what theta is, now we have to find out what v and t is. Which one would be easier to find first, v or t? Huh? T, because of the equation, right? Because of this second equation here, right? See, t is going to be given in terms of the other ones. Okay, so here go, let's solve for t. Go. I didn't get there yet. I'm going to repeat it. That's what we did in math, right? System of equations. That's exactly what we're doing here. I'm going to pass the square root to the other side. Here we go. I found t. And now that we found t, we can find v. Okay, substitute on the other equation in the other equation upstairs, and solving for v. Let's see what we can do. Yeah, let's see. Here in Word, I can give you I can have the luxury of writing the second equation over and over again, right? Doesn't take much energy to do that. I'm going to cancel the m, and I'm going to pass the r to the other side. I'm gonna take advantage of this v square here and write down the r square in its place. Here you go. R square. I don't want it bold-faced. Right, here you go. Ooh. Like that. So we can go one more step. Did I make any mistake? Doesn't look like. I can take the square root. Okay, the square root of the r squared is going to become r. I'm going to write down L right in here downstairs. And I don't need, and we have the square root of a square root. It's kind of awkward, but we do have it. Okay, so that's our answer. V and T. Okay, it's 5:43 now. Let me take attendance. Any questions about that?
Well, Professor,
Uh-huh.
on your book, is it saying that on the denominator where it says that L radical 1 minus R divided by L,
Let's see.
there's another one, it just says 1 minus R square root.
Let me see. Let me see. My book. Let me check. Maybe it's just a different format.
I'm looking at from page 120.
Yeah, let me see. What, for the V, right?
Or B, yeah.
Okay.
Right
I
there.
put L. Oh, yeah. Okay, I know how I did it. Yeah. Let me see. Yeah. Uh-huh. Yeah. You can. It's just a different format. I can put this L here inside, becomes R L square, and the L and would be L square here as well. L square cancels out with this L square.
Oh, okay,
And we reduce to the same value, right?
the same value.
Exactly the same equation. Here you go.
That makes sense.
Okay, so here you go. L, I want a square. I'm gonna, here you go. I'll use this one here. Okay, I'm gonna put a parenthesis here. Simpler. L square, change it. And then, I don't need to write this L, right, on the outside, because I passed it to the inside. And it's the same thing here. No, here is not the same thing. Yeah, here's not the same thing. But what I can do here, I can put under the common denominator and pass the L upstairs. Okay, that's another way. I'm not gonna do that. I'm just gonna, okay, now this L square goes right in here. This one goes right in here. Okay. Okay, and then we end up with R square only. And I don't need the parentheses anymore. And now we have the same equation that I have in my notes. Okay, so any more questions? Let me pause it now, right? Remind me to recording, right? Good. So let me take a look here. What's the next example in the book? Okay, so we're going to do the case of a car negotiating a curve, okay? So here you go. Here's the case of a car that's negotiating a curve. Suppose that, there is no grip in the road, okay? Suppose that he's driving in a icy road and there is no traction whatsoever, right? What's going to happen? What's going to happen? He won't be able to negotiate the curve. What's going to happen is that he's going to shoot tangential to the curve. Okay? The car is going to just follow the the path of the velocity vector, the direction of the velocity vector. That's what's going to happen. Okay, so here you go, just like that. I'm gonna put one more here. That's what I mean by playing the movie. Oh gosh, you get it? Nope, not what I want. This one here. Good, now I got it. And I'm gonna move this guy. Oh. Yeah, the velocity vector is gonna get out of there. I don't like that, but that's okay. Yeah, yeah, like that, right? So, so we can use physics to find out what would be the maximum velocity of this car in a road, not necessarily in an icy road, but in a regular road that still have some friction there between the tires and the pavement. We can do that. Okay, so suppose that you know the radius of curvature of the curve and you want to know the maximum velocity. And let's take a look here at this. Okay, a car of mass m is undergoing uniform circular motion on a flat surface of radius r. Let me see if that's the one. Oh yeah, find the maximum speed so the car can negotiate the speed the car can achieve to negotiate this curve safely. Okay, so the idea here, the car mass m, uniform circular motion, a flat surface of radius r. You know the value of coefficient of static friction. Find the maximum speed the car can achieve in the curve safely. Okay, so what you know the mass, you know the radius, and you know mu sub s. So let's do that. Another problem on uniform circular motion. A car in a just like the exits that we take in the freeway, right? You know, some exits out there they tell you to slow down to 25 miles an hour, right? Those 25 miles an hour. Why is that the 25? Because the curve is very sharp. Okay. What does it mean? The curve is very sharp. It means that the radius of curvature of the curve is very small. Okay. The larger the radius of a curvature, the easier it is for you to negotiate the curve. Okay. So they are taking into account the safe limits of exiting that the freeway. Okay, so here you go. Given the mass of the car, the radius of curvature of an exit in the freeway, and the coefficient of static friction between the tires of your car and the pavement. Okay, given the mass of the car, I'm gonna put it m. The radius of curvature of the freeway, I'm gonna put the lowercase r. And the coefficient of static friction. Notice that I'm talking about coefficient of static friction, not coefficient of kinetic friction. There's a reason for that. Can you picture the reason? If the car is moving, how come we're talking about coefficient of static friction, right? Can you picture why is that? There's nothing wrong with that, by the way. Simple. Here you go. Find the maximum speed can go to negotiate this curve safely. Solution. Okay. Oh, you gotta do the drawing, right? You already saw the drawing here. But that's not the exact drawing that I want. I want more than that. I do know that there is a centripetal force in there if I want to keep the car moving along this curve safely. Okay? If he's going too fast, he's going to shoot tangential to the curve. Okay, so what's the drawing you're gonna make? You're gonna make this drawing here. Okay, you're going to identify all the forces in the car. Here you go. Let's start here. X, Y axis, X axis, Y axis, car, and then 1, 2, 3 forces, right? So let's do that. Play the movie again. I didn't put X and Y. X axis, Y axis, the car without the forces. I didn't put the radius yet. Here you go. Okay, next one. I think I'm gonna need one more. Here you go. No forces there. But the position of the car, radius r from the center of curvature. The center of curvature is right in here at the origin of my coordinate system. Okay, you know the force, the free body diagram. Every time you want to solve a problem using Newton's law, you have to have a free body diagram. The first force that you're going to write down is going to be the weight, the force that's always there. Okay, a little bit off center, you know, it's supposed to be right in here. I'm putting here so you can see the radius of curvature. The other force that you're going to identify is going to be the normal. Okay, and remember that in order for the car to safely negotiate this curve, it must be subjected to a centripetal force. But do you see a centripetal force here? Did I draw any force that's going to be the centripetal? That's the net force. Okay? I have to draw one more force here that is going to be your centripetal force. Okay? In order for this car to negotiate this curve, I'm not going to put the centripetal force. The right way is to put it the net force. That would be the right way of writing that down. Okay? So I must, you have only vertical forces here. I did not identify any horizontal forces whatsoever. But I do know that this car, in order for it to negotiate this curve, it must be subjected to a net force pointing towards the center of the curve. Okay? So what is this mysterious force that I haven't found yet? That's what you have to ask yourselves. What is this mysterious force that we haven't found yet? Okay? I already gave you a hint. If there is no friction whatsoever, if it is an icy road here, is the car gonna be able to negotiate this curve? No, right? There must be a force of friction for you to negotiate a curve in the freeway exit. Okay? There must be a force of friction. If there is no force of friction, he's just gonna pass by straight. You're gonna crash right in there. You're gonna lose control of your car and so on, right? So the force, the mysterious force that's missing, is going to be a force of friction. I'm gonna translate this one right in here. Okay, and I'm going to rename it here as force of friction. Okay, I'm gonna take out this, and wait a minute. And now the question is it a force of static friction or is it a force of kinetic friction? That's the question that you have to ask yourself. Is it a force of static friction or is it a force of kinetic friction? What do you think is gonna be? Okay.
Isn't the max force?
Well, let's go by step, right?
Okay.
Is it a force of static friction or kinetic friction? That's what you have to ask yourself. Okay.
Okay.
Does a force of kinetic friction has a maximum value?
Kinetic.
Huh?
Kinetic. I mean,
Does it have a maximum value? That's what you gotta ask yourself. Let's see here. I'm gonna get this one here. There he go. That's the net mysterious force, right? And then I'm gonna do another slide here. Think about that. Here we go. This one. And you should be able to justify why one and not the other. Okay. Here you go. Let's play the movie again, right? Here you go. X-axis, y-axis, the car, the distance to the center of curvature. The first force is the weight, the second force is the normal. We do know that in order for the car to negotiate the curve, it must be subjected to a net force that's supposed to be a centripetal force that points towards the center. Okay, that's what we know. The question is, what is this force? I already told you that we must have a force of friction. Okay, and this centripetal force is going to be a force of friction. Now the question is, what is which force of friction is going to be the force of static friction or the force of kinetic friction, right? Either one or the other. Force of static friction or force of kinetic friction. Then you have to justify why. Which one will that be?
the kinetic.
Why?
Because it has a more movement control on the vehicle.
Because the car is moving.
Yes, moving, but it's controlling the wheel.
Okay, so now let's ask. The car is moving the forward direction, right?
Right.
Is it moving in the central direction, in the radial direction? Is it moving the radial direction? In order to negotiate the car, that does it move in the radial direction? So here you go. Here's the circle, right? Think about the circle. It's like that, right? It's definitely is moving in the tangential direction. But is it moving the radial direction? It's circular motion. Does the radius change during a circular motion? Does the radius change during a circular motion? Okay. The tangential, the tangential in the tangential direction changes. The motion changes in the tangential direction, right? But what about the radius? What about the radius of curvature? The car stays here in this radius, right? The distance to the center is going to be the same, right? Because the distance to the center is going to be the same, the radial component of the velocity is going to be what? The radial component of the velocity is going to be what? The tangential definitely is, no, is different of zero. But about, this radius, is this radius changing as time goes by? Is this distance here from the center changes as time goes by? Huh? It will change if the guy, right? In this case, that there is no friction, the radius to the center of the curve is changing, right? See that?
Right.
Right? But what if the car stays in the circle? Does the radius change? Does the distance? No. Okay, the radius doesn't change. So the velocity in the radial direction is equal to 0. Make sense? Not in the tangential direction, but in the radial direction is equal to 0. So if I'm going to draw, here you go. If I'm going here's the one you want to see, right? If I'm going to draw the forces on this car, I have to put my force of friction here in the place of the centripetal force, right? Here you go. I have to put my force of friction here in the place of the centripetal force. Now the question is, what type of centripetal forces, or what type of frictional forces? Well, because the radius doesn't change as time goes by, it means that the velocity in the radial direction of the car is going to be 0. If the velocity in the radial direction of the car is 0, so it means, and this force is pointing towards the center, so it means that this force can only be the force of static friction. Okay, that's not obvious. That's not obvious. Okay, at this point in time would be the force of static friction. Another point in time, here you go. The car is going to be at another spot. Ooh, going to be another spot right in here. I'm going to rotate it a little bit, like that. Okay, the velocity is going to be pointing the other direction. The force of static friction is going to be pointing towards the center. But the dVdr is not changing. No, sorry, the drdt is not changing. Because the rdt is not changing, this force of friction must be the force of static friction. Okay. So that's the key to solve this problem. We should be tempted to classify that as being the force of kinetic friction because the car is moving, right? But the car is moving in the tangential direction, not in the radial direction. Okay, the radial distance to the center is going to remain constant. So it is though as the car is at rest in the radial direction. The car is at rest in the radial direction, not in the tangential direction. Not in the tangential direction, but in the radial direction he is. He is at rest. Okay? And we also know that the force of static friction has a range of values, right? We know that the force of static friction have values between 0, right? And what? 0 and what else? And a maximum value, right? Those are the range of values of the force of static friction. So we're just studying the problem, just preparing to solve it. So here you go. Now I can go back to this one here, and I can tell you for sure that it's gonna be the force of static friction. I'm gonna put like that, static friction, not kinetic friction. And the force of static friction has values, has a range of values. Okay, we have this one too. Let's see here. Let me get, yeah. Why am I repeating that? Okay, here you go. I put there at the top of the car, static friction. And I'm going to put it here a little bit down. And this thing should be applied to the tires of the car. Okay. Okay, and now we can start looking at the equations. We are going to note solution, equations, Newton's second law. Here we go. I'm gonna use those. True. Single vectorial equation. Net force in this case is gonna be equal to the normal, the weight, and that mysterious force, which is the force of static friction. Let's see how I can do that. I don't, yeah, I want the X there because I'm going to put the S here. Okay? Vectorial format. Then we translate that in terms of the X and Y components. What did I do here? Okay, X lowercase f s comma x, and then we do that in terms of the vertical component as well. We go y direction, y direction, y direction, and gotta ask yourself whether there is a centripetal acceleration along the y direction. Okay. So let's go to the next. Now you gotta look at, find out if do you have any zero components. Okay, do you have an x component for the normal? Yes or no? Do you have an x component for the normal? No, right? What about x component for the weight? No, right? So we're gonna go ahead and cancel that x component for the normal and x component for the weight. Then we're gonna go back and see if you have any y component of the force of static friction. Do you have a y component for the force of static friction? Does this force of static friction has any component along the vertical direction? The answer is no, right? So here you go, put a 0 here as well. Is the car moving along the y-axis or just along the horizontal direction? The car is not moving up and down, right?
No.
So we must have a 0 acceleration along the y direction. So here are, oh no, I didn't do that. I should have done that. Yeah, I'm gonna copy it. That's okay. We're in good shape here. I didn't lose anything. Here we go. That's the order supposed to go. Okay. In the next equation, I'm going to simplify. I'm going to get rid of my zeros. Okay, here we go. Get rid of those zeros. And I'm going to substitute my weight. My weight is mg with a negative sign. Okay. And remember, what else you have to know? You have to remember that the force of static friction has a range, right? Has a range of values. And I'm going to include that in as a third equation. Just be reminded that the force of static, I'm going to put here as being the second equation. The force of static friction is going to be greater or equal than 0 all the way up to a maximum value. 0 and less or equal than a max. I'm going to put it this way. Like here. I can drop the x subscript now to simplify the... Yeah, I'm gonna drop it just to simplify the notation. I'll drop it here and I'll drop here. It became but now I'm going to rewrite as being a maximum value. Here we go. Okay, remember that the force of static friction has a range of values. That is a very important step here. This one is a very important step. Okay, what else? I'm gonna put one more. Yeah, better. Okay, I don't want this one here. Okay, good. All together. What else can we do? Okay, I can put the value of the force of static friction. You remember the value of the maximum force of static friction? The value of the maximum force of static friction is mu sub s times what? Times what? Go back to your times n, the normal, right? And the normal already found out. What's the value of the normal? Okay, and by the way, you know the n sub y doesn't have any any x component, so we can simplify this equation to n. We can simplify this one to n as well. Because we are going to need the value of n, we can solve for n in this third equation. Right? Here you go. I still didn't touch the first one. I still didn't touch the first equation. Now that I know what the normal is, I can substitute it in the second equation. Here you go. mg. And now I don't need this third equation anymore because I have already used it. Okay? So now I have one equation and I have an inequation. Remember that I told you what's the maximum value of the velocity for the car to negotiate the curve safely? This car must have a velocity anywhere between 0 and a maximum value here. That's going to be given by this upper limit. So what I'm going to do, I know that force of static friction is m times centripetal acceleration. I can plug it right in here. Okay, but I'm going to do something else too. I'm going to do something else too. I'm going yeah, that's okay. I'm not going to do anything. I'm just going to plug it straight forward right in here. Yeah. Okay. I'm just using the equality in the first equation in the inequality of the second equation, right? Force of static friction is equal to m acceleration, centripetal acceleration. So I can plug the centripetal mass times centripetal acceleration right here where this force of static friction is. Okay, and now that I already used up the first equation, I don't need to repeat it again. And I can here write my centripetal acceleration as what? Just like we did before, v squared over r. Let's see if I have it here. Yeah, right in here. So it saved me to go hunting for the superscript and up and down and subscript. Here you go. It's gonna be lowercase r. That's what the centripetal acceleration is. Okay, and see here. Okay, now I have an inequation that goes anywhere between 0 and a maximum value. I'm going to pass the m to the other side. Whether I pass to the left or to the right, the m is going to disappear. Here's going to be m divided by m. Here's going to be 0 divided by m, right? And I'm going to pass the r to the other side as well. When I pass the r to the other side, in the right side it becomes 0 because you're multiplying 0 by r. In the left side it becomes mu s g r. Okay? So now I learned that v squared has a possible range of values. The minimum value of v squared is going to be 0. The maximum value of v squared is going to be mu s gr. Okay, so what's going to be the maximum value of v? All you gotta do is take the square root on both sides. Whether it's here or there, here you go. Here is going to become square root. And the square root of 0 is 0, right? Those are the possible ranges of v. Minimum value is 0, maximum value is this square root here. Let's see if we can, let me see if I have a numerical example for that so you can have an idea what it means. I don't think yeah, I didn't do a numerical value here. Okay. But let's play a little bit with the numbers, right? Let's take a look at the coefficient of static friction between a tire and a concrete. Coefficient of static friction. Coefficient of static friction. Table. Let's see now, not here. Let's see. Table. What time is that? 6:43 already. Table of coefficients of static friction. Clean and dry. Look at the engineering toolbox. Tire and concrete. Concrete. I don't have concrete here. Maybe I have concrete down there. Tires. Okay. Huh, no tire. Rubber. Oh yeah, rubber. Okay, dry concrete. Okay. Rubber, dry concrete. Between 0.6 and 0.85. Is that static or kinetic? Kinetic? Huh, it doesn't have static? What a shame. Yeah, it doesn't have a static. Okay, looks like they didn't measure. but they measured in asphalt, dry asphalt, 0.9. Strange not having concrete. Shouldn't be difficult to calculate that. But they have for asphalt, 0.9. Okay, let's use 0.9. Note that the maximum velocity does not depend on the mass of the car, right? The mass cancels out before. Okay, numerical example. Mu sub s equal to 0.9. Mu sub s equal to 0.9. Oh, what's a good radius of curvature of a curve? Let's take a look at the internet. Let's see. Radius of curvature of freeway exits, right? Exits. What are reasonable values? Yeah, the radius of curvature and exit ramp of freeway. Okay, this one is 750 feet. Let's see if we have 64 meters. Let me see. Yeah, 64 meters is less than 750 feet. Okay, multiply that by 3. Yeah, this one is more like 200 feet. Okay, so let's use this 64. Oh, I'm gonna use 60. Let's use a. You know what? Let's use 64. Yeah. Okay. R64. No. R equal to 64. We're going to meters. We're going to use G, 10 meters per second square. Okay. Script. Okay, like that. And let's go to Excel. I'm gonna plug in all those numbers. You can do this calculation very quickly. It's gonna be a square root. What times that? 647. There's the time, right? 3 more minutes to do that. Equal square root 64 times 10 times 0.9. Okay, 64 meters times 10 meters per second square. Take this square root, you get meters per second. I get 24 meters per second. 24 meters per second. Let's change that in terms of miles per hour. Okay, 24 meters per second. Okay, we're gonna do meters per hour. That's meters per hour. Okay, 86 kilometers per hour. Okay, divide that by 1,600 and we get miles per hour. 1.6, 1,600. 54 miles an hour. Okay, if you exceed 54 miles an hour in a curve that's 64-meter radius, you're not going to be able to negotiate it safely. Okay, so it looks like the curve is not that bad because going at 54 miles per hour in a curve is pretty fast, right? So let's finish here, right? And we have a lab right now. We're going to do Newton's second law for the Tuesday students. And I see you upstairs.